Hello everyone, welcome back to the tutorials again. In previous sessions, we have studied about the examples on consolidation. So I would like to continue with the examples, few of the complicated examples, few of the examples from your question papers, few of the examples from competitive exams I would like to solve over here. So you can see over here an undisturbed soil sample. It is given over here, an undisturbed soil sample that is clay 24 thick, consolidated 50% in 20 minutes. Consolidated 50% in 20 minutes when tested in the laboratory under drainage allowed at top and bottom. So this particular line I have marked purposefully so that you can able to understand the meaning of this line properly. So there is a double drainage which is provided because as we are allowing the drainage from top as well as drainage from bottom, so it is double drainage. The clay layer from which soil has obtained is 4 meter thick in field. So clay layer under test is 24 and clay layer in the field is 4 meter thick. How much time it will take to consolidate 50% with double drainage? If clay stratum has only single drainage, calculate the time required to consolidate 50%. Assume uniform distribution of consolidation pressure. Assume uniform distribution of consolidation pressure. So H in the laboratory is 24 H in the field is 4 meter. This we have to note down. Time for 50% consolidation in the laboratory is 20 minutes. Time for 50% consolidation in the field is what we have to find out. But for that also there is the condition. For double drainage in both uh, lab and field we have to find out. In double drainage in lab we have to find out, and for single drainage in a field we have to find out the time required for 50% consolidation. So there are two cases. In first case, in lab also and in field also double drainage is allowed, but in second case, in lab double drainage is allowed and in field single drainage is allowed. In both the cases we have to find out the time taken for consolidation. So we know that T is directly proportional to H square divided by CV, where H square is thickness of the layer. CV is, what is CV? CV is uh, what is CV? CV is the formula for CV is given over here. You can see CV is coefficient of consolidation. So time rate of consolidation is directly proportional to H square divided by CV. CV is coefficient of consolidation, H is thickness of layer. Okay, so we'll move back to there. So the problem which we were studying was this one. So both the cases, CV will remain same for all the types of soil. So entirely T is directly proportional to H square because CV will remain same for same type of soil. So in lab also we are using the same type of soil, and in field also there is a same type of soil. So CV will remain constant, or it will not going to change. So T is directly proportional to H square. So thickness, time taken for consolidation is directly proportional to thickness and drainage conditions. So you can see, I can say that T2 divided by T1 is equal to H2 square divided by H1 square. So what is T2, what is H2, what is T1, what is H1? So H1 is the thickness of the layer in the lab, H2 is thickness of the layer in the field. So H in lab is 24 divided by 2, that is 12 1.2 centimeter. H in field is 4 meter divided by 2, that is 2 meter, that is 200 centimeter. Just conversion I have did. So first case I am considering double drainage, that is why I am dividing it by 2. Next, T2 is equal to T1 into H2 square divided by H1 square. So T2 is time taken in the field, which we need to find out. We have time taken in the laboratory. So time taken in the laboratory for 20%, 50% consolidation is 20 minutes. So T2 is equal to 20, T1 into, that is 20 into 200 divided by 1.2 whole square, that is 5,55,555.55 minutes is required. So first case is over. For double drainage in both the lab and field, the time taken in the field for 50% of consolidation is this much. So I am converting it into days. 385 days approximately is going to come. So T2. Now double drainage in lab and single drainage in field. So as we are allowing the double drainage in the lab, so which is equal to 24 divided by 2, 12 mm, that is 1.2 centimeter, that is double drainage. Single drainage in the field, h is equal to 4 meter, it will remain same, that is 400 centimeter. So T2 is equal to, same formula I am going to use. T2 is equal to 400 divided by 1.2 square into 20. It is going to give us 2 lakh 22,222.22 minutes. So if I convert it into days, 1544 days are required with the single drainage in the field. So you can observe one thing over here in the problems. If we provide the double drainage, the consolidation is very much fast. If we provide the single drainage, consolidation is very much slow. So consolidation is entirely depending upon the drainage condition which we provide. So just try to understand the importance of drainage condition. I'll just briefly repeat this problem. So what they have given thickness of a soil layer in the laboratory. Even they have given the thickness of soil in the field. So in the laboratory they have conducted the test and they say that for 50% consolidation it takes 20 minutes in the laboratory. But in the field, what is the time taken for 50% consolidation they are asking. So in both lab and field, in first case, in both lab and field, they are providing the double drainage. In second case, in the lab they are providing double drainage, and in the field they are providing single drainage. So this is the thing which we need to find out. So case number one, in both the cases there is a double drainage. Then T is directly proportional to h square divided by Cv. So in both lab and field, same type of soil is there. So Cv will remain constant. So T is directly proportional to h square. So same relation we are going to use. So T2 divided by T1 is equal to H2 divided by H1, H2 square divided by H1 square. So here T1 H1 is the lab condition, T2 H2 is the field condition we are going to consider. So T2 is the thing which we need to find out. H for double drainage we have already calculated. Similarly, H for single drainage also we have already calculated over here. So in same way for double drainage as we calculated, we are going to apply the uh, quantities and we are going to find out the answer. So finally we are going to convert it into days. Similarly, for double drainage in the lab and single drainage in the field, we are going to apply. So just you must be very much careful. I'm sorry. You must be very much careful in applying double and single drainages. So finally we are going to get the answer for these two things. Next, this problem is a little important and it is from previous year question papers. An undisturbed sample of clay stratum 2 meter thick was tested in the laboratory and average value of coefficient of consolidation was found to be 2 into 10 to the power minus 4 centimeter square per second. Average value of coefficient of consolidation, CV. If structure is built on the clay stratum, how much long it will take to attain the half the ultimate settlement under load of structure? Assume the double drainage. So half the ultimate settlement. So half the ultimate settlement means T50, means 50% consolidation. Half the ultimate settlement means when 100% consolidation is going to occur, at that time ultimate settlement is going to occur. But when the 50% consolidation is going to occur, at that time 50% settlement is going to occur. This point you need to note down. Okay, so what they have asked, if the structure is built on the clay stratum, how long it will take to attain half the ultimate settlement under the load of structure. And assume double drainage. So h is equal to 2 meter, that is 2 divided by 2. 2 I am doing because it is a double drainage condition. So 1 meter, that is equal to 100 centimeter. CV is equal to 2 into 10 to the power minus 4 centimeter square per second they have given. Now we know that CV is equal to TV into h square divided by T. So TV at 50 into h square divided by T50. So TV is equal to uh, for 50% drainage, for 50% consolidation, we need to find out TV. So TV is equal to pi by 4 U divided by 100. So U is degree of consolidation, that is 50%. So 50% divided by 100 into whole square into pi by 4 is going to give us the value for TV. So this value for TV we are going to substitute over here. But you have to make sure one thing, that we are calculating it for half the ultimate settlement, means for 50% of the consolidation, which is going to happen only in case when the consolidation is 50%, when the consolidation is 50%. So T50 is equal to TV into h square divided by CV is going to give us 9.85 into 10 to the power 6 centimeter. So in days it is 114 days. So it is very important. Just ultimate, this point is very important, half the ultimate settlement. So they have tried to confuse you by taking the name of settlement. They have not directly asked the time taken for 50% consolidation. They have indirectly asked it, and they said that half the ultimate settlement under the load of structure. They have asked half the ultimate settlement. So we have to consider 50% as a consolidation. Next you can see uh, this is from consolidometer test. This example is from consolidometer test. So you can see here it is from June 2013. A consolidometer test on clay showed decrease in wide ratio from 1.37 at 100 kPa to 1.25 at 200 kPa. Means wide ratio was decreased from 1.37 to 1.25 with increase in stresses which we apply, or load which we apply, that is 100 from 100 kPa to 200 kPa. This was the increment in load or stress which we apply. Now thickness of the sample at 100 kPa is 20 mm. Coefficient of permeability is 5 into 10 to the power minus 7 mm per second. So thickness of sample at 100 kPa is 20 mm. So initial thickness only we have to consider. So in case if they give thickness of a sample at some 200 kPa, don't consider that. Initial thickness only we have to consider. So conversion is very important over here. 1 kPa is equal to 1 kilonewton per meter square. So directly 200 kPa is equal to 200 kilonewton per meter square. 100 kPa is equal to 100 kilonewton per meter square. We have to consider. Next, what we have to find out? We have to find out coefficient of volume change, that is MV, compression index, that is CC, coefficient of consolidation in mm square per year, that is CV. Coefficient of consolidation in mm square per year, that is CV. Next, initial stress which we applied is 100 kPa. Final stress which we applied is 200 kPa. E1 is equal to 1.37. So initial wide ratio, final wide ratio is 1.25. So H0 is equal to H, our final thickness of the layer, is equal to 20 mm. So K, coefficient of permeability, they have given as 5 into 10 to the power minus 7 mm per second. Mm per second they have given. MV we need to find out. CC we need to find out. CV in mm square per year we need to find out. They specifically mentioned mm square per year they need. So in mm square per year we need to calculate it. Let us move one by one. Coefficient of volume change, first I would like to calculate, that is mv is equal to E2 minus E1 minus E2 divided by 1 plus E naught into 1 divided by sigma 2 dash minus sigma 1 dash. So E1 in this case is 1.37 minus 1.25. So initial wide ratio is nothing but E1, or else I can call it as a E0. So both E1 and E0 will remain same in this case. If they specifically mention E0, we have to consider it as a different one. So 1.37 minus 1.25 divided by 1 plus 1.37 into 200 minus 100. So it is going to give us 5.06 into 10 to the power minus 3 meter square per kilonewton. So this is the value for MV. So MV we have got similarly compression index, that is CC, E2 minus E1 divided by log 10 to the base sigma 2 dash divided by sigma 1 dash is equal to the values I am going to substitute. 1.37 that is E1 minus 1.25 that is E2, sigma 2 dash that is 200, sigma 1 dash that is 100, that is stress increment was from 100 to 200. Okay, so Cc is equal to 0.3986 meter square per kilonewton is the answer I am going to get. Next, coefficient of consolidation in mm square per year. This is the quantity which we need to find out. So mm square per year we need to find out. You can see over here K I am going to convert it to meter per second. Later I can convert it to mm. So meter per second is mm to meter, that is into 10 to the power minus 3. So total will be 5 into 10 to the power minus 10 meter per second. So K I have converted. CV, for CV I have the formula like this: K divided by mu W into MV, which is equal to 5 into 10 to the power minus 10. MV is 9.81. So meter per second I have converted. Substitute this mu W as 9.81, which is kilonewton per meter cube, into MV they have given. So MV is 5.06 into 10 to the power minus 4. They have we have calculated, that is meter square per kilonewton. So same I have substituted and I have got the answer for CV as 1.007 into 10 to the power minus 7 meter square per second. So just if I want to convert it, I can convert it to meter square per year, then I can convert it to mm. So the conversion is given over here. So if I want to convert it, if I want to convert the seconds to year, then I have to divide the denominator by 365 into 24 into 60 into 60. So I am dividing the denominator, so once it goes to numerator it will be like this, and if I calculate it, it is going to give me the answers in meter square per year. Then I have to convert this meter square to mm square, that is 1000 square. If I do, I am able to convert it to mm square, that is 10 to the power 6. So first of all, 10 to the power 6 I have multiplied to convert this meter square to mm square, and to convert the seconds to year I have multiplied it with this quantity. You can just calculate it. Hope you have understood. In next session we are going to move further to the important problems which we are going to solve. Even we are going to solve few problems from your question papers also, few problems from compaction also we are going to solve from previous year papers, and we are going to end up with this particular unit. So we'll stop here today. Thank you.